So every interpreter for a Lisp-like language, including Scheme, does type tagging of the data this way that we're talking about internally. Some other languages don't do that, and this is why it's worth talking about and not a trivial idea, because there are implications either way. So in that language you learned in high school, you say things like integer, I comma j, and maybe you say float or something, x comma y, right? And you will have noticed this semester that there isn't anything like that in Scheme. You don't have to say when you create a variable by define or let or whatever, what kind of value goes in it. Okay, whereas you do in these other languages. Typically languages that are mostly compiled rather than interpreted make choices like this, meaning that you write your program and you run it through a compiler and out comes a machine language program which you then run, as opposed to something like Scheme where you type in an expression and out comes a value and you type in another expression and you can interact with it. So why do they do this in these languages? What it buys them is this. Computers have these different representations, the conventions about how to interpret the bits built into their hardware. So in whatever computer you're using, there's going to be an instruction, typically with a name like add, and another instruction with a name something like floating add. Okay? And because of these declarations, if you say I plus j, the compiler for Java or C++ or whatever it is you learned knows that it should do integer add. Whereas if you say x plus y, the compiler knows that it should do floating add. Right? And therefore, at compile time, we already know what kind of arithmetic to do. And we can compile this into exactly the right machine instruction. Scheme doesn't know that. When you say something like I plus j in a Scheme program, we don't know until the program is running what kind of thing the value of those variables is going to be. Right? Because in Scheme, you can make a list of numbers, and some of them are integers and some of them aren't, and it all just works. Okay? So the disadvantage that we get from using type tagging, in other words, from associating types with values rather than associating types with variable names, the disadvantage is that our programs run a little slower because the Scheme interpreter sees, well, it doesn't see I plus j, it sees plus ij. And it has to say, well, let me look at I and see what its type tag is. Let me look at j and see what its type tag is, and then do whichever of these is right. By the way, what if you say I plus x? What happens? Well, something more complicated, because you can't, the machine doesn't know how to add an integer to a float. So what happens is you call a procedure that says typically convert the integer to a float, and now I have float plus float, and then I can do the computation. And the compiler has to think about that case also, as does the interpreter. Right? But the compiler does it before you're even running the program. So if you're in a situation in which you're going to write a program, and once it's written, it's going to be used every day until forever by some company, then it's a good idea to put as much of the work as possible on the shoulders of the compiler. Because when the program is running every day, it then doesn't have to do this kind of analysis. It's just ready to roll. On the other hand, at kind of the other extreme, if you're, let's say, a student in a computer science class, basically your programs never go into production. You're only interested in a program as long as it's not working, right? And once you get it debugged, you go on to the next exercise. So for you, what's important is not the running speed of your program so much as the running speed of the whole process of reading what you type and figuring out what it means and doing it. So we don't really suffer from this time efficiency problem of using typed data instead of typed variables. And we get an advantage. The advantage we get is this. It's really easy to do heterogeneous data. Okay? So I can come over here, and I can make a list that contains an integer and a non-integer. It's not going to remember all those digits probably. And a word and a list. And that just all works. Okay? If this were a list of numbers, I could write a little program to add them all up, and my program wouldn't have to worry about is this thing an integer or is it not an integer? Right? So what you have to do in this kind of language is stuff like okay? Since variables have to have their types set ahead of time, if I want to write a procedure to square a number, I have to write one for integers and a different one for floats, and I have to call the right one for whatever kind of number I'm actually looking at right now, and it's a big pain in the neck. Okay? If you know that in this program you're only dealing with integers, then it's okay, or only dealing with floats. But if you're going to try to mix types, you end up doing stuff like this. Some of those languages, because their designers aren't idiots and they know that nobody wants to do this, invent sort of mechanisms on top of mechanisms to let you type both of these at once by having essentially a variable for the type that you then give, you know, first you say do this for integers and then you say do it for floats. But that's the sort of thing that we get for having types attached to data, is that we can have heterogeneous data. We can mix things up, and it doesn't matter. Okay? So that's a little piece of sort of programming language design questions. Because one of the things I'd like you to get out of this course is to be able to answer the question, why isn't there just one best programming language? Okay, this is part of the answer. Right? The best programming language for writing a program once and then running it 1,000,000 times might not be the best programming language for the process of development. And in fact, there are companies out there in the world where they'll use something like Lisp in the early stages of developing a product, because they can come up with new versions and tweak up the user interface and so on and get it just right. And then finally, when everything is just the way it's supposed to be, they'll re-implement it in something like C or C++ or Java so that it runs fast. Not so much Java fast, but the other ones run pretty fast. OK, so that's the story on type tags.